Well, welcome back to Mechatronics 1. Today we are going to talk about semiconductor electronics. And semiconductors are really the foundation of modern life. All of your electronic devices run on semiconductors. And today we're going to learn a bit more about how that happens. So, last lecture, I think we kind of wrapped up some components. We talked about how we use those components in circuits, and then we talked about breadboards and troubleshooting, and how do we kind of use components. And that was really kind of the first phase of the class where we talked about some of the basic electrical engineering kind of introductory ideas. And now we're going to kind of transfer into some more modern things. And we're going to start with semiconductor electronics. So we're going to talk about semiconductors and then diodes, LEDs, and then some of the circuits we can make with these components. And then we'll follow on next lecture will be Apollo. We'll talk more about some of these ideas and continue to develop them. So you can see the video here. We do have three videos in today's lecture. Some of this content I think is fascinating. Some of the way that these things are made, and so I think it's good to have some videos to go through it. Semiconductors, what are they? Why are we talking about it? Why is it important? Well, semiconductors, like it says, it's not a conductor and it's not an insulator. It's a semiconductor, and so it's kind of in the middle. And one of the things that we can do with semiconductors, we can tailor them. We can adjust their properties to make them more or less conductive, how they become conductive. We can design devices to take advantage of that. Um, the probably the most common material for these semiconductors is silicon. It's cheap, it's easy to be made. There's other materials that you could use, and it really depends on the application. Germanium, gallium arsenide are two other popular materials, but by far and away, I think silicon is the one that is used the most. So let's take a look at a video here. And I think that's fantastic. Can you imagine the 1,500 steps to make one chip? I mean, that's a fantastic. I think it's a great video, and we've got a couple more we'll go over here today. So, what does this mean? And we'll see a video more about how this works. What we do is you have a semiconductor, but it doesn't have all the properties that we want. And so what we'll do is we will dope these, make an extrinsic semiconductor, and we add impurities to it to get the properties that we want. N-type semiconductors are doped with phosphorus and arsenic and antimony and some others. And what we're doing with the doping is we're adding extra electrons. And P-type semiconductors, we are doping with boron and aluminum and gallium, and we're creating holes. And so you need a hole and you need an electron. So electron will jump from its current material into the hole in the other material. So yeah, it's a fantastic thing. And let's take a look at how this works in a little more detail. Once again, I think it's a good video that kind of shows this layer by layer. And so you've seen now they've implanted one layer, they've applied some photoresist, they've masked, they've applied copper, they've grounded, and this process will continue. And you build layer upon layer till you get the final circuit diagram that you're trying to create. So it's a pretty amazing process. And this is what they're creating. So you have this P side of this semiconductor that's doped and has holes, and then you have the inside. This is the cathode side. It has electrons, and there's no charge added to it. Nothing's really happening. You have this depletion region where it's kind of a barrier zone where things can't happen. But if you add a little bit of voltage to it, then you can get the electrons to move to the other side. So it acts like a switch. And that's really all these PN junctions are switches. Now, for silicon, it takes about zero point 0.7 volts to overcome the depletion zone. It's zero point 0.3 volts for germanium. You also have a thing called reverse bias, where if you apply, you can see this is a voltage source, and um, uh, let's see, I just hit the wrong way. You can see that the direction of the electron flow is this way, current is this way. If you do it the other direction, so you can see the plus is on the other side of the voltage source, you create a reverse bias. And reverse bias creates a barrier to electrons flowing. So current in one direction creates conduction, and current in the other direction will create a reverse bias or a wall. And this is really the basis of a diode. You if you apply the voltage, you can overcome that depletion zone and it flows. Reverse bias creates a wall, and then there's this thing, a breakdown voltage. And a breakdown voltage is if you just apply enough current, enough voltage to the system. If you're applying enough voltage system, you can just overwhelm everything and break the diode and make it, um, and it just stops working. And so they have special ones that are designed to do this called Zener diodes, but we really won't talk about that much, but just to make you aware. And this is what these silicon diodes look like in real life. And here's kind of the schematic, a PN junction. It also looks like this. You have a schematic symbol of what it looks like. And this is for ICs. These are packaged devices will actually have like what the part number is on it. And there's usually an arrow showing the direction of bias. So here's another quick little video that kind of shows you how this works. So I think that's a really good video that kind of shows how that works. One of the keys there that I think I didn't realize until I did the math was he says the transistor is about 22 nanometers wide. And if you think of a human hair is in the ballpark of 100 microns wide, so what you're talking about is 450 transistors is the width of a human hair. That's how small these things are, and you can see why there's 100 million in your phone or a billion in your laptop. Light emitting diodes, to move on to the next topic, is um, a type of PN junction. Let's see, I've got this out of line. There it is. And what they are, you have a P and an N junction, you put them together. The materials is different. And what happens is a photon of light gets emitted when the electron crosses from the one side to the other under forward bias. So um, light is emitted basically. So and different colors of light come from different materials. So it's not that a different amount of power creates a light, and you'll see that this can be a bit confusing. So a red LED, for example, takes 2 volts of forward bias to get the electrons to cross the depletion zone and hit the other side and then emit light. Blue takes 3 volts to cross the depletion zone and recombine and let off photons of light. It's not the voltage that it gives you the different colors, it's different materials that give you the different colors. It just happens to be the different voltages that are required for these different materials. Another thing that's just something to remember is you will need a resistor in series to prevent too much current from burning out your LED. So that's an important thing to remember. Um, and what do we use these things in? Let's look at a few devices that use these diodes. One's a half-wave rectifier. So you've got a voltage source, a resistor, and a diode, and voltage out. And this type of circuit, the voltage in is a sine wave, the voltage out is this rectified wave. Another one is the flyback diode. So if you have a switch, especially with a motor in the circuit, you'll need this flyback diode, and it's a voltage source, a switch, an inductive load, the resistor, and this flyback diode. And what happens is in normal operation, everything's running. You've got this just a steady state current. And without the flyback diode, if you don't have a diode here, when you open the switch, what happens is you get this change in current over time, and you get this huge spike of current, and then it settles down and depletes over time. And this huge spike destroys everything. Everything explodes into pieces and burns out and all kinds of problems. And so you put this flyback diode in here so that you get this nice current. And then when you open the switch, it just an exponential decay down to zero current. Just a way of protecting your circuit. So I think this is a good introduction to semiconductor electronics. We talked about diodes and LEDs and some of these interesting ways you can do them. I think it's a good start, and we'll continue to talk about semiconductor electronics next week. So thank you very much, and I'll see you next week.